Welcome to Six Sigma Black Belt, Course 5, Module 1, Measuring and Modeling Relationships. Now that we have laid the foundations of Six Sigma, we are ready to begin inferences. Our first topic will be inferences surrounding correlations and predictions. The linear correlation coefficient measures the strength of the linear relationship between the paired x and y values in the data set. Correlation ranges from -1 to 1. Note that correlation is not the same as slope. While these two values will agree in sign, they will not agree in magnitude. A positive value of correlation coefficient implies that the line slopes upward to the right. A negative value of the correlation coefficient implies that the line slopes downward to the right. Note that r equals 0 implies no linear correlation. This does not mean that another type of relationship does not exist. Correlation is a very complex calculation. When finding a linear regression, correlation is typically also calculated. The correlation plays a critical role in our determination of the linear regression. Correlation is like a measure of dispersion about the best fit linear line. As the data spreads further away from the line, the correlation coefficient drops. The coefficient of determination is the proportion of the explained variation divided by the total variation. It is the correlation coefficient squared. It ranges from 0 to 1. Coefficient of determination is a measure of the amount of variability in the process that the model is capable of explaining. Note that correlation does not imply causation. There are many examples in the real world that exhibit strong correlations, yet any causal relationship cannot be concluded. An example would be the likelihood of getting a speeding ticket and the brightness of the color of your car. It is well documented that cars with bright colors, like red and yellow, tend to attract more attention. It stands to reason that if you owned a bright red car and you were in a pack of cars that were speeding, your car would be more noticeable and pulled over with greater likelihood. The process for finding the confidence interval of a population correlation, ρ, requires a Fisher transformation. Because correlation does not follow the bell-shaped normal distribution, we need this transformation. Correlation is in fact negatively skewed. First, we convert the sample correlation to Z prime using the Fisher transformation noted here. Z critical prime is based on a normal distribution. Zeta is the transformed population parameter from the population correlation ρ. N is the number of pairs of data. Once we have the lower and upper limits of the confidence interval, we can then transform the Z prime back to a correlation. For example, suppose we wish to find a 99% confidence interval about a sample correlation of 0.732, given 46 pairs of data. Z prime will be 0.933023. Z critical prime will be 2.5758. This gives us a lower transformed limit of 0.5402 and an upper transform limit of 1.3258. After we transform back to R, we get 0.494 and 0.868 respectively. Therefore, we are 99% confident that the population correlation will be between 0.494 and 0.868. Behind every correlation, there is a hypothesis test. The existence of a significant relationship between y and x can be tested by whether rho is equal to 0. When conducting a hypothesis test for correlation, the null will be that the correlation is 0, and the alternative will be that the correlation is not 0. Because correlation is negatively skewed, we again need a transformation to a student's t variable per the formula shown here. We can then compare this test statistic to the critical statistic. If the magnitude of the test statistic is greater than the magnitude of the critical statistic, we will reject the null hypothesis. The critical t statistic is based on the alpha, 1 minus the confidence level, and the degrees of freedom, n minus 2. For example, suppose we wish to determine if a sample correlation coefficient of 0.312 is statistically significant using 99% confidence level and 46 pairs of data. The test statistic is 2.1783. The critical statistic will be 2.6923. This is with 44 degrees of freedom and an area in the tail of 0.005. Since the test statistic is not bigger than the critical statistic in magnitude, we fail to reject the null. There is not a linear relationship present. Even though the correlation is clearly different from 0, statistically speaking, it is not significantly different from 0.